Record. Sorry. So getting back, I forgot to record the earlier part. But yeah, anyway, so here I'm trying, so I showed you how to construct the affine matrix by giving it this source and destination points and applied it on the image. Now, anyone knows, so if I want to go for the homography, like what is different from the homography? Let's see. Let's see. Yeah, I see people in the chat. So Rachel says parallel lines are maintained. Okay, so parallel lines are maintained in the affine. That's actually a very good point, Rachel. While in the homography, not necessarily. Like you will find it's not necessarily to be maintained. So that's a good point. For the image, okay, so the term compression, it's a bit like it could be mislead to another thing because compression can be just like quantizing, for like quantization, like trying to make the image like smaller in the file size. I mean, so that might not. I'm assuming this is not what you mean, Miriam. But if you mean that it is.
Yeah, that is like is narrow. I don't know how to explain. I know that compress can be like JPEG and so on.
Exactly.
Compressing the dimension, but I'm saying like I don't know how to explain this in English. Like is basically the proportion change.
Yes, so this proportion, yeah, exactly. So this proportion because of the non-isotropic scaling. So this is what the affine will do. But here's the thing, the homography does allow non-isotropic scaling as well. But the homography has an additional feature, like it's almost like I'm not sure if you see me in the camera, but it's like going from one 2D plane to a completely different 2D plane, and then showing how it appears from this perspective. So on the affine, you don't do that. So for example, there could be some skewing. So let's see actually one example here. This is still an affine. I can just go through it quickly. This is just doing a flip, like flipping the image. So again, it's the same operation of just doing horizontal flipping. Now continuing on the homography. So I want to show you how it becomes a transformation from one 2D plane to another 2D plane. So remember, homography is 8 degrees of freedom. So we need to define at least 4 points. We cannot just use 3 points. So we're going to use the 4 points, the 4 corners of the image. And then we're going to transform. So we have here the target points. These are just simply like transforming so you see here, this is the top left and the top right are going to go to the same. So they won't change. But what will change is the bottom left and the bottom right. They will transform based on this target, these defined target points. So now we have 4 source points, 4 target points. Now it's not affine anymore. So we're gonna use the get perspective transform function. And the projective matrix is not going to be just 2 by 3 anymore. It has to be the full 3 by 3. We always estimate the homography up to a scale, meaning that this last term is 1. That's why it's only 8 degrees of freedom. We talked about how these are like kind of ratios. Now, if we take this, let's just go through it. So if we take this projective matrix, and then now we're going to warp perspective. It's not warp affine anymore because we have this 3 by 3 matrix. And we give it our image and the final width and height of the output image. You see here, it becomes almost like this kind of perspective distortion. It only happens with the homography. So this happens, it's sorry, just to clarify what I mean. I mean that it appears, so it's not just doing some shearing or stretching. It's not just going beyond the similarity to have non-isotropic scaling. It goes a bit beyond that, like it can allow some skewing effects. It has this like going from one 2D plane again to another 2D plane. So you can think that it actually like you did some transformation to get the image to look on a completely different 2D plane, and then how you like from your perspective, what would be the image. So this is what a homography would do. So yeah, I mean, I hope this explains it better. But let me know if you have any questions. And we're gonna actually like do a couple of exercises on the transformations now. But yeah, I'm checking if there are any questions here. Okay. So let's say I have here, this is some journal with the Sudoku. And I actually have defined my, like I want to remove perspective distortion from this Sudoku to get this final image. So you tell me what would be, so again, it's first, what would be the transformation that I'm going to use? Like, can I use just an affine? Or what transformation do I need to use? And what would be the source and the target points? Similar to what we did in the previous transformations. What do you think? Any, again, don't shy out, it's okay. I mean, we're again, like we're refreshing our knowledge together. If this is new to you as well, it's okay. That's the whole point of the mentorship sessions anyway. So if I want to do, but it's important to participate because it helps me also to know if there is an issue that I need to address. So it's okay. So if I want to do remove perspective distortion, like I have this full image here for the Sudoku, and I want to just have only the rectangle for the Sudoku, and removing also perspective distortion, like you feel like it's as if the journal is viewed like it's a bit behind, right? Like it's like laying on a table and you're viewing it. I want to put it like orthogonal. So what do you think I should do? Yeah. So Asala, yeah, exactly. So we're gonna use a homography, great. But can you help me, Asala? What would be the source and the target points? So what exactly would I use to send to the get perspective transform? Asala or anyone else, I mean, it's okay. What would you use for the source? So for the source, meaning the original from, this is like image 1 and this is image 2. So in the source, what would I use for the source points? What do you think? Yeah, suggestions. I can you can even like again, don't try out. It's okay. Like a huge shout out actually for the people participating. I appreciate it. Anyone wants to suggest?
Okay, I want to make a suggestion.
Yeah, of course. Go ahead, Rachel.
So the source points would be the green dots, the edges of the Sudoku puzzle.
Exactly, the corners. So these 4 green dots. Exactly. So that's the source. What would
Yeah.
you do for the target?
So the target ones, since you want to crop the main part out, the first corner would be 0, 0, and then plus the width of the image. That would be the x of the first corner, and the y will be 0, 0, and then for the next corner, it will be the x will be the 0, 0 plus the width of the image, and
So
then
so you mean for this corner, this will be
yeah,
what again?
no, this will be 0, and the x will be 0, and then the y would be the width of the image.
It's the reverse, so we always
It's the
top
reverse.
left. It's okay, but yes. So you can have like so whatever the number of columns and then 0. So this will be the second point. Yes. And again, this one, so thanks Rachel. And then this one would be the number of rows. So 0 and the number of rows. So always remember that the top left is our origin. But yes, that's exactly. And the number of rows and the number of columns you can actually compute by simply going through. So if you try to take the difference between these original corners and get the maximum, you can already estimate what would be the maximum width and height. So with these simple operations, you can, that's what we're doing here. This is just kind of hard-coded for simplicity, but these are the corners. We assume this is just like 300 by 300. It doesn't actually matter, like you can, at the end, it will stretch it to like fill in the 300 by 300 image. So this is what Rachel was saying. Like we have the origin 0, 0, and then we have here the number of columns 0, 0, number of rows, and so on. And then you get perspective transform, and then you warp perspective. So this is the second one. And then here, so this one I'll leave you like just let's say 10 minutes, and we can and then we can discuss it together with the solution. So this one is an exercise that I want you to try. So this exercise, what we're trying to do, we have an image, a black image that has this, you see this rectangle here and this center. So this black image with square, this function already like draws for you the points and the lines, like the rectangle. So this is already ready for you. And the center, these are like the top left, like the corners of your square that you're plotting here. And then we have this transform, like a make transform function that will take the points and apply the matrix, whatever, it doesn't have to be a rotation matrix, by the way. So this is, you can just, you can here send any transformation matrix and it will apply it to the points. And then draw it again to construct the final image. So here you will take a copy of your image. So this will draw over the original image and then compute the new points. So the new points will be taking each point multiplied by your matrix, take the resultant point as an additional point, and you're gonna go through all of the points and apply it. And then we're gonna do like draw the lines, the points and the lines, and in our new image. So, and then return both the new image and the new points. Okay, so these are already provided for you. You don't need to implement anything there. So this is something I'm trying here. Like if I just want to rotate with 30 degrees. So remember, so yeah, clockwise, if I want to go clockwise, I will do positive. Remember when we said that it's flipped? So this is here positive. If I want to do anti-clockwise, I will do negative, but this is just again because of the image that it is flipped coordinates. This is not the normal. So this is here showing if I just rotate with 30 degree and construct the rotation matrix. Now remember, when we talked about how I can do if I want to transform around the center of the rectangle. So you have here the center point. So this is the center point of the rectangle. I already have it defined for you. So what you need to do is simply, I want you to write the code that will rotate this matrix, this square, sorry, around its center with 30 degrees. So I like try it yourself. So you will need to define your translation matrix, your rotation matrix, and then apply it, and then like taking it back to the original position. And this will be like your output should be something like that. So you have your original rectangle and then the rotated one around the center with 30. So yeah, I mean, let me make sure first that this is shared. I mean, I already shared it on the Slack. Let's see. Yeah. We'll Colab 2 again here. So yeah, I mean, in case if anyone has any issue on how to access that Colab, let me know. but I sent it already on Slack. So I want you to try it from here. Yes. So the complex transformation part, you can ignore everything else. So if you go to the complex transformation part, you can start running from here. You might just need to run the first, this first one that is importing CV2. Otherwise, you don't need anything else. And yeah, I mean, I'll leave just 10 minutes and then we can discuss the solution together. Yeah, I mean, I'll just bring some water and get back to check how you're doing with the collab. Okay. I mean, again, I just left 5 minutes, I know, but I wanted to check, anyone having any issues or things are going smooth? Anyone have tried to run it? Like, do you have a suggestion on what to put for the translation matrix? Any questions? What do you think? Okay.
Hello.
Yeah. Hey, Grace. Yeah.
Hi, Dr. Mina. Please, did you include the image on Slack?
Oh yes, let me do that. But for this one, you don't need the image. But yes, just 1 moment. I'll add it. Actually, that's a good point that we need to.
Thank you.
Yes. So I just sent it, Grace. Thanks. Thanks for letting me know. But for this part, you don't really need, you can take, like you can comment out, you only need to import CV2. So you don't need, you only need these 3 lines. Otherwise, it's not really important. Yeah, I see another, oh, okay, no worries, Grace. So yeah, once you reach here, yeah, starting here, you can run without needing the image, but we can actually discuss it together now. If you have already implemented it, that's great. If not, we can just discuss at least the concept. What do you think we should do? So if I want to rotate around, like I want this resultant image where I have a rectangle and another rectangle rotated by 30 degrees around its center. So how to draw this rectangle? So if I start first with like transforming to the origin, what do you think would be the translation matrix in this case? So remember, I have 1, 0, tx, I have 0, 1, ty, and I have 0, 0, 1, right? Regardless of the code now, what do you think I should be putting for the tx and the ty?
Negative 250.
Exactly. So we will have negative 250 and negative 250. Thank you. Exactly. So this, if you do this, this will result to making the, like moving to the origin. So this is the first thing we need to do. And then we have here the rotation. So what would be the rotation? That's an easy one. Just, what do you think? Anyone remembers the rotation matrix? Okay, let me tell you. So it's cosine 30, negative sine 30. You get used to it once you, and then sine 30, cosine 30. Once you get used, I mean, once you work more with transformations, then 0, 0, 1. So this will be the rotation matrix. And then you need to translate it back. So this will be the same, but instead of 250, negative 250, we're actually going to have 250 instead. So let me actually show you here the solution. So here, if I do this, oh, I'm not sure if I have to run it all over. It's okay, I can just show it to you at least. So this is again what we agreed, like moving with negative 250 in the x and the y, and then rotating. So cosine, negative sine, sine, cosine with 30, and then doing the translation back, and this will give you the resultant image. So you can, yeah, you can experiment with this at your time. If anyone has any questions, I'll proceed. Well, let me see on the chat. So yes, sorry, Omar, I just saw your message. So I'm assuming yes, you mean with the center point, the one that will be used for the translation, exactly. So yeah, I mean, if no questions, I will continue now with how to actually apply these transformations on images. We just saw warp affine, warp perspective, but what does image warping actually does? And it's the same. So it's the same operation in PyTorch. You will find the like the corresponding methods that are doing the like the warping, and you even define whether it's bilinear or bicubic or what, or nearest. So we're going now to learn about this image warping operation. So for image warping, if you have normally what I showed you, like we have some transformation matrix. It's a 2D, so we have 3 by 3. I apply it on a 2D point, x, y, and then 1, because we're working in the homogeneous coordinate. But I never told you how to apply it on a full image. Like I have a full image here, and I want to apply it on every single pixel to get this resultant image. So there are two types. There is forward warping, where I start from the original and go to the output here. Or there is inverse warping, where I start from the output and use the inverse of the transformation to retrieve what I need from the original. So the forward warping, let's say I have my input image here. So I'm gonna transform every pixel. So I have whatever the, like, let's say this is a pixel. I mean, just for illustration. So I have one pixel here, another pixel here. So each one of them, I'm going to take its location. So it's 0, 0, and then 1, 0, and so on. So we're gonna take this, multiply it by the like our transformation, whatever the transformation is. It's some 3x3 transformation matrix here. I'm gonna multiply it by 0, 0, 1. It will get me an output, let's say 2, 2, 1, let's say. So this means that it's in the location pixel 2, 2. So I'm just going to put here the color. So this is like the most straightforward thing to do, right? So I'm gonna, here, I'm gonna put the color that is here into here. This is one operation. So this is the forward warping, like the simplest thing. I'm gonna take every pixel, multiplied by the, take its location, multiplied by the 3x3 transformation matrix I'm doing. And then the output will be the output location of this color for this pixel. Now what happens if your output is not exactly a pixel, meaning it's so we're looking for subpixel. So I have, let's say, yeah, I mean, we'll see that you can do some approximation. We can just do a nearest, like the simplest thing. We can just do a nearest integer pixel. So if I have 21 and 20, after the transformation, it became 21.7 and 20.2. And then I have another one, 22 and 20, which is again, after the transformation becomes 28.8 and then 20.4. So if you approximate both, you will see that both got transformed. So you have 1 point, let's say this. So I have 1 point and another point, both transformed to the same location. So now if you both are in the same location, it means there will be some holes as well here, because there will be some pixels here. Let's say, like I mean, this is just again an illustration, but you might end up with some pixels that have 0, like no source point got mapped to it. So you will end up having, instead of, this is not a forward warping, like usually we use inverse warping, but I'm just using it as illustration. So you might end up having in your image here, let's say multiple ones that got mapped to 1 pixel, and then some pixels in the output that had 0, like not a single pixel got mapped to. So you end up with these holes, and this is something we want to avoid. So we usually don't use forward warping. I'm just motivating why we're going for the inverse. So this holes is the main issue that we're trying to avoid, and why we'll go for the inverse warping. So for inverse warping, we do the reverse. From its name, we start here from the target, and then I know the width and the height of the target. This is actually given, and I can compute each pixel here in the target. I'm going to get its location. So now it's the target. So I'm gonna have, let's say here 0 and 0 and 1. And then I'm gonna multiply by the 3x3 transformation inverse. So it will map me back to some location here. So there's no way there will be holes here anymore, because you literally go through each pixel in your output, try to map it back to the source image. So let's say I took this 0, 0, 1. After I did the inverse transformation on it, it became 2, 2, 1 as well. Like again, as just illustration. So I'll just go to the 2, 2, 1 pixel, get its color, and fill it here. Something along that line. Okay, so this is what will happen in an inverse warping. So again, we're in the inverse warping, we use the inverse of the transformation that I'm trying to do. Now, if I have points that are subpixel, like it's not exactly 22, it's 22.5, or like instead of 23, it's 23.8 after. So if I have here x, y, 1 multiply by t inverse, and I end up having x bar, y bar, 1. This x bar, y bar ended up to be with this decimal point, like 22.5, 23.5. This is in between pixels. So you go to the neighboring pixels and do the interpolation. So that's what we define. Like, yeah, this is what why in the, you can do nearest. So the nearest will just take the nearest integer. The bilinear will, and this is what is like, it's defined linear in, whether in Torch or CV or OpenCV, is what we will see now how to do. It's very simple. Like 22.5 lies between 23. 22 and 23, right? And then 23.8, this lies between 23 and 24. Okay, so we're gonna see how to do the interpolation simply. So we have here again 22 to 23 on the x and 23 to 24 on the y. So these 4 neighboring pixels are what I will use to actually compute the location 22.5, 23.8. And I have the corresponding intensities of these 4 pixels. So now I'm just doing the subpixel, like for like how to compute the intensity of this 22.5 and 23.8, because it's in between pixels. So I have this here, and I have the corresponding intensities. So now I will show you how to compute the intensity, the final intensity of this in-between pixel. So you see 23.8, let's do, so the bilinear interpolation means we're gonna interpolate the term bi, because we're gonna do interpolation on the y, interpolation on the x, or like the x first and then the y, it doesn't matter. So in the when I interpolate on the y, let's say I started with the y first. So this is between 23 and 24. So 23.8, it is closer to 24, right? Like we have here, if you look into the distances, so this is closer. So this will take the higher weight, and this will take the lower weight, and both have to sum up to 1. So the closer pixel, because we at the end I have this 23.8. So I know in distance at least, so this is a 0.8 distance and this is 0.2, but then the weight of the closer distance should be higher. So that's why I'm giving it 0.8 and then 0.2, okay? That should be like, again, standard interpolation. So we have, if we're taking, this is the 40 and the 43, 40 get multiplied by 0.2 because this is the further apart pixel, and 43 gets multiplied by 0.8 because this is the one that is closer, okay? So this is here one interpolation, and I end up with this, and I'm gonna do the same. So I did interpolation here. I'm gonna do the same here as well. So this is again taking 42. So this multiplied by the 0.2 because it's further away, and 50 multiplied by 0.8 because it is closer to me. So this is here. So now I have 2 output from doing the interpolation on the y, like on this here and on this here. What remains is to do interpolation on the x. So we have 22.5. I'm gonna take exactly, it's the in between. It's like half. So I'm gonna take half this value, half this value, and this will be the final output. So the final output is just simply taking 0.5 multiplied by 42.4 plus 0.5 multiplied by 48.4. This is because it's in between. It's like exactly 22.5. So in between these, in the middle of between these two. So this 45.4 will be the resultant value for after doing the bilinear interpolation. Okay, so this is the whole operation. What you do is that you take, let's say these are the output pixels. Each output pixel, I'm gonna go map it. using the inverse of the transformation and get the corresponding value using whether bilinear interpolation or nearest interpolation, whatever you define. Now I'm going to ask you something, because you see this, understanding this simple thing can help you to avoid, for example, one of the bugs, like I think, Rachel, you were saying that you're interested to go for segmentation. So let me ask you, if I have an image and its corresponding segmentation ground truth, okay? So I have here, this is a ground truth for the segmentation, and I have here the image itself. And I want to do some operation that is doing scaling, rotation, and so on. So I'm going to do I have some transformation here, T. What would be the type of interpolation you will use here versus here? And it's not necessarily Rachel only, sorry, I'm talking generally. Like it's something that I'm trying to motivate you why, for example, having this understanding can help you avoid small issues when you're coding your deep learning model even. So anyone knows? So if I have the image, what type of interpolation? So here we talked about so far bilinear, bicubic, and nearest interpolation. I didn't tell you what is the bicubic, you can ignore. But we talked about the bilinear and the nearest. So what type of interpolation will you use here versus here? Any suggestions? So I'll type it here, like 1 bilinear, 2 is the nearest. And let's start with the image. So if I'm applying a transformation and I'm warping the image itself, would you use 1 or 2?
In the example you wrote, was the GT?
So sorry, Miriam, can you repeat again?
In the example you wrote, was GT.
Oh, this is ground truth.
Okay.
Yeah, I'm sorry if it's not clear. So we have the original image, just the original image as is, and the ground truth segmentation. So the ground truth segmentation, let's say I'm doing like a foreground segmentation. So I have only the face as 1, for example, and everything else is 0. For simplicity. So everyone is like saying, so I see Loyan and Mimziara and Grace, you're saying bilinear, and that's correct. Bilinear is more accurate than nearest. So you're better off because bilinear, you actually take, like you benefit from all your neighboring, like the 2 by 2 neighboring pixels. So if you're doing it on an image and you want everything to be as crisp as possible, keep it bilinear. And it's still efficient than the bicubic, that's why. Now let's apply the same, I wanna do the same warping operation, like the same transformation, I mean, on the image, because you know, you have to, like if I'm going to rotate this image, do some scaling, it has to be applied exactly to the segmentation ground truth. Which interpolation would you use? Would you use the bilinear or the nearest? So 1 or 2? What do you think? You can take a guess, it's okay. So would you use 1 for bilinear or 2 for the nearest for the ground truth segmentation? Anyone wants to suggest? Yeah. Again, don't be shy. So Grace, you're saying bilinear as well. Okay. I understand your point. I mean, bilinear is more accurate, right? So that I get that from that point, but keep in mind, so this is the tricky part. The ground truth segmentation is categorical, right? We're doing classification, but it's pixel-wise classification, but it's still the output. Can I have in the output, let's say I have here my output after the rotation for the ground truth, can I have pixel value 0.5? Like, does it make sense? So I have 0 and 1. I have only category 0, 1. So if you do bilinear, you might end up with values that are in between because you're interpolating, right? It is more accurate, but the problem is that it doesn't become categorical anymore. So at this point, you're just better off using the nearest, because with the nearest, it will just take the nearest pixel, and will take its value as is. So you can never, like, it will always be, it will stay. So it's, the input is categorical data and the output is still categorical data. Just because so you can either do this, or at least make sure that you transform the output from the bilinear interpolation to be categorical. So it's either this or this, but yeah, just using the right interpolation from the start is easier. So anyone has any issue, like why so here, it's better to use the nearest. Here, it's better to use the bilinear. Anyone has any issue with why? Everything is good? Okay, cool. Thank you. Thank you, Miriam. Thanks, Idris. Okay, so if this is good, we have covered actually the basic part of the 2D transformations, and I think the remaining will be, now we can go to the 3D. We will not do the practical for the 3D today, but we at least will go through some of the slides for understanding the 3D transformation. So yeah, this part here, yeah. So in the remaining part of this hour, we will be going through understanding the 3D transformations and like a better understanding of camera models. So we are trying to look into how, if I have a full 3D world point, how to project it to pixel coordinates, but in detail. So remember, we did take the pinhole model, but we didn't take more, we just like took the outlines. So this time we're gonna go through the details. But in order to do that, we need to understand some of the, like, we're gonna go through the same transformations, translation, rotation, the Euclidean, the similarity, all of these, but in 3D. So remember, with the translation now, because I have my input X, Y, and Z. So these are operations that are happening in the 3D world now. It's not just 2D. So I have a full X, Y, and Z. And I have point that I want to translate to a destination point. So I'll have a corresponding translation in the X, in the Y, and the Z. And everything else in the transformation matrix stays the same. If I want to do the inverse of the translation is as simple as just doing the negative of that. So I'm gonna translate with negative tx, negative ty, and negative tz. Okay. So again, it's very simple to the 2D. That's one is hopefully is good. How many degrees of freedom you think this will be? So if we're talking about degrees of freedom. Yes, I see. Yes, Miriam, exactly 3. So we have 3 degrees of freedom that we can control, which is the tx, ty, and tz. Thank you. Now, if I go for the rotation, now the rotation in 3D is it's much more complex. Now we're not just rotating around a certain point. You actually need to define which axis you are rotating around. Okay. So you see here, this I just rotated around the z. That's not necessarily what you should do. You want to do with the rotation. You might want to instead rotate around the y or rotate around the x, right? So each will have its own rotation matrix. So now we have something to keep in mind, which is the axis to rotate around. So if I am trying to rotate around the z, you will see that, so this is the transformation for it. And you will see that the z actually stays the same. So the ones that are going to undergo the transformation are the x and the y coordinates, while the z coordinate will stay the same. So here, this is the cosine, negative sine, sine, cosine, and it will get multiplied only by the xy, and these are the ones that will get rotated. Why is this the case? So let's do it step by step. So if I have here my input, some cuboid, and I have this point x, y, z, and I want to rotate around the z-axis, okay? Now, if I rotate around the z-axis, you will see here, if this is, for example, height 2, let's say I now like drew it so that this is the z-axis, okay? So if this is 2, like z equal 2, here, Z is maintained as 2 still, like nothing changed, right? Like this part didn't change. What rotated was applied only on the X and the Y. And that's why you will find that here it's 0, 0, 1, 0. So the Z gets multiplied by 1. Nothing changes. So whatever, and this is actually applied across all, whenever you're rotating around an X, whether it's the Z or the X or the Y, the one that you're rotating around, its coordinate doesn't change. Yeah, its component doesn't change. So let's see actually on a, yeah, okay. Before we go into like if I wanted to show you the Y and the X as well, like rotating around the Y and X, but before that I want to just confirm one thing. So here, when I do cosine, negative sign, sine, cosine, I'm rotating with this angle, alpha. Now, if I want to do the inverse of a rotation, an inverse of a rotation, what do you expect I will do? What should I do? I'm rotating, so rotating with angle alpha. The inverse of this is just rotating with angle, as simple as this. What do you think? It's a simple one, like don't over think it. So I'm rotating with, like if I have here, and I'm rotating with angle alpha. Now I want to do the inverse of that. So the inverse of that will just be rotating with negative alpha, right? I see someone responded. So exactly, Asala, thank you. Negative alpha. So this is how you would do it. So rotating with negative alpha, and this is the inverse one, is just cosine, sine, negative sine, cosine. And these are like simple trig rules you can remember on your own. Yeah. So the inverse, which is just rotating with the negative of the angle, you will see it's actually a form of just doing a transpose. Now, why? You always, it's always important to remember that rotation matrices are orthogonal, meaning that each column and each row is, or like each column is orthogonal to the other columns. And the same for the rows as well. I think it's actually orthonormal. It's not just orthogonal, meaning that, if I remember correctly, yes. Meaning that these are also unit vectors. Like you can, each one of these is also a unit vector. Now, why I'm telling you this? Because orthogonal matrices, the inverse is the transpose. So if I have, so I'm showing you here, this is R with alpha. This is R with negative alpha, or like what we call as the inverse of alpha, okay? So this inverse, you see cosine, negative sign, it just got transposed, sorry. So if you take R, multiply by R inverse, you expect the identity. With an orthogonal matrix, if you take R and the R transpose, you will also expect identity. Because they are orthogonal, right? So if you take any row here, if you take any row here with and do a dot product with this column, yeah, I mean, if it's just one moment, yeah, if it is itself, it will be 1, but otherwise, because they are orthogonal, it will just be 0. Okay, because dot product of two orthogonal vectors is just 0. Does it make sense? So just showing you something like a property of rotation matrices. So rotation matrices are orthogonal matrices, meaning that the inverse is the transpose. And we know that, so any orthogonal matrix, if you take it and it's transpose, multiply by each other, it becomes the identity. So that's why our transpose is our inverse. So here, just want to show you the final, exactly. So inverse is the transpose. So this is just the transpose of this one, right? Okay. So anyone has any issue with this property in rotation matrices? Everything is good? Yeah. I mean, it's sometimes it can help to know, to keep these, I know this kind of linear algebra refreshers, like usually you might forget, but it's important to keep it in mind, because you will find it easy when some of the people will just refer to it and use it as is. So now that we know how to do the inverse of the rotation, which is simply doing transpose for the matrix, and now I'm going to show you how to rotate around the other axes, so whether the y or the x. We did the z-axis, so we saw how to rotate around the z-axis and how to do the inverse of that rotation. We're gonna see here the y. So the y, this is, again, remember, if I'm rotating around a certain axis, so this is the y, it stays the same, doesn't change. And I showed you that in the z, so it's exactly similar here. The rest, which is the x and the z, these are going to rotate with the cosine sign as we agreed. And this is how it is. If you note that it's just for the rotation of the y, so this is cosine beta, negative sine beta, and then sine beta, cosine beta. The reason it is constructed like that, you can, if you want to prove it, you can actually plot, and you will see that it is like similar to how I proved it before in the 2D. You can do it here, and if you want to understand why this is the matrix, but this is, yeah, I'm just giving it to you. This is how to rotate around the y-axis. If I want to rotate around the x-axis, again, x stays the same, and the y-z are the ones that are going to rotate. So cosine, negative sine, sine, cosine, as normal. Okay, so now we have the full rotation composing the rotation around all the axes, the z, the y, and the x. If you multiply all these rotation matrices together, you end up with your final rotation matrix. And this is the parameterization that is called Euler angles. Because you see here, this is this alpha, beta, gamma. These are Euler angles. These are sometimes referred to as like pitch, roll, yaw. So for people working, if you are working in robotics or interested to go for robotics, it's also good to know these terms. So this alpha, beta, gamma, these are the Euler angle parameterization. There is different parameterization for doing 3D rotation that is better than the Euler angles, but you don't have to go through, like it's more advanced. So for people who are like going deep into 3D vision or robotics, they might need to go through these, whether quaternions or X-angle representation. And I'm referring to, so Zaleski book, the book itself, I'm referring to it in the first slide. It's a very good book, and it's open source. You can all download it like full, download the full book. He's an amazing guy. So here, I'm going to revisit all the transformations now that we know how to do the translation and rotation, which is the core ones that are different. We're gonna visit everything, but now in 3D. So the translation, it is simply just an identity and then adding our translation vector tx, ty, tz. So we agreed this is 3 degrees of freedom. For the Euclidean transformation, which is a rigid transformation, so it's only including rotation and translation. So this is here a 3x3 rotation matrix and our 3x1 vector, translation vector. And it preserves the lengths. But how many degrees of freedom do you expect? Yeah, what do you think? How many degrees of freedom for the Euclidean transformation? Any suggestions on the chat? So we have 3 degrees of freedom for the translation. Miriam has helped us with that from the previous slides. For the rotation and the translation, how many degrees of freedom you think? Think of it, this 3x3 matrix is the combination of rotating around the x, the y, and the z. So then how many degrees of freedom? So we have the 3 from the translation plus how many for the rotation? Any suggestions? If you feel like I'm going too fast, let me know also. Or if you wanna do you want us to have a break? 12, okay. So 12 for the rotation y. So how many angles? If we're doing the Euler angle representation even, how many angles do you have, Omar? Exactly, thank you. So if I have 3 angles, we just discussed that parameterization that I have, the Euler angle parameterization, I have mainly, sorry, I don't know why. So I have mainly the alpha, the beta, the gamma, the pitch, roll, yaw. So you can think of it that I have 3 angles, 3 like the tx, the ty, the tz for the translation. So you can end up with 6. I don't want to show off all of them, but you end up with 6 degrees of freedom for the Euclidean. Now for the similarity, remember it is isotropic scaling. And it will maintain, even in the 3D, it will keep isotropic scaling. Isotropic scaling meaning that's the same scalar factor across all the dimensions, x and y and z. It doesn't preserve the length. So whatever here is 2 centimeters, for example, is not going to be the same because we just did scaling, but it preserves the angle. So if this is 90, after the transformation, it still maintains 90. So how many degrees of freedom, you think? Any suggestions? So I have here, this is a 3 by 3, and this is a 3 by 1. So in total, like this matrix is a 3 by 4. And how many degrees of freedom? 7. Thank you, Rachel. Exactly, 7. Because we just added a scalar factor, and it's just one scalar factor for the isotropic. Thank you. And then we have the affine and the projective. So the affine, what do you think with the affine? So this matrix here, what is its size and what is the degrees of freedom? If you know its size, you will know how many degrees of freedom we have. And I think, Omar, you might have confused this with the rotation. So this matrix is how like what is the size of this matrix for the affine, which allows for non-isotropic scaling? What do you think? I'm always showing you. So I see sorry. Oh no. If you, I was always showing you that we are multiplying by, so we have here, these are full 4 by 4, like this matrix here is 4 by 4, but if you cut out this part, which is always going to be 0, 0, 0, 1 in an affine, so this remains 3 by 4, right? Except now it allows also, like you can have some non-isotropic scaling happening in your transformation. So if you have 3 by 4, you end up having 12 degrees of freedom. And the parallel lines stay parallel. But the angles you see change. So something that was 90 degree got changed into something that is not necessarily 90. So anyone has an issue with this? How many degrees of freedom here? And then the projective, this is when, again, but this is in 3D. So we have 3D homography and we have 2D homography. We talked about the 2D homography. What do you expect here? So this is how, like, what is the size of this matrix? This is the full projective transformation in 3D. It can get multiplied by any x, y, z, and 1. And it will transform it accordingly. So what do you think? This matrix is, what is the size of this matrix? Any suggestions? I mean, I can leave you to think about it. Remember that the 2D homography, it was a 3 by 3. This is for 2D. Now that I'm going 3D, what do you expect? So this was multiplied by x, y, 1. Now I have x, y, z, and 1. So it's 4 by 4, exactly, but with 15 degrees of freedom. Thank you, Rachel. Exactly. Why? Because similar to here, we had 3 by 3, but then we only cared about the ratio, so we have only 8 degrees of freedom. So similarly, we have here 15. So this is the final like a transformation hierarchy. Yeah, we still have time, so that's great. We can still go through the camera models, hopefully. Anyone has any issue on the 3D transformations before I go through the camera models? No, everything is good. Okay. So for camera models, we're trying to see how to project from 3D to 2D. That's the whole idea. You can do orthographic projection. Now, orthographic projection, it actually means that you completely ignore the depth. And x is equal to x, y is equal to y, and that's it. So this is here the 3D, and this is here the projected 2D. And this is the matrix for doing the orthographic projection. It's very simple. Just take the x as is, take the y as is, and we completely ignore the z. And we just, the homogeneous coordinate is taken as, like you take it as is as well. Okay, so this means, for example, if I have these squares and I have, you're trying to do orthographic projection, it just becomes small, like if we take this cubes, sorry, it just becomes these small squares because you completely ignored the depth, like any depth component here. This is like if you have a camera that is almost has no perspective effect because it's, for example, like very far away from a scene, like on a very high altitude UAVs, you can use orthographic projection. But again, it depends also on the type of the camera. Like, I mean, again, it's just a way to describe specifically how to take from 3D point to 2D point. Okay. Now, if I go for the perspective, and this is where you will see that, so remember here in the orthographic, this line here and this line here is parallel. After the projection in 2D, these stay parallel as well. Now for the perspective projection, not necessarily. You will find that these lines start to become to seem like they are converging. For example, you know, take this image of a road. I know that the road is parallel, right? Like I have some sidewalk here. These lines in real life, in 3D, they are parallel. But they seem as if they are converging because of the perspective effect. So you will start to get lines to converge. And that's part of the perspective projection. Now, to describe the perspective projection, like we need some projection matrix here. Once it's multiplied by the x, y, z, 1, our 3D, then it can project it into this 2D x, y, 1, x bar, y bar, 1. Okay, so what is this projection matrix? This is what we're going to cover. How to construct the matrix. So this matrix is 3 by 4 because it has to be multiplied by the x, y, z 1. So we're always working in homogeneous coordinate, and it will result into the x bar, y bar, and some omega bar actually. So this one, it might differ after the projection. Okay. So let's see how to construct this P. And for that one, let's do a refresher a little bit on the pinhole model because we will start with this one. So I'm showing you here, I have a camera. The location of the camera is called, I'm gonna call it the camera center. I have my image plane. So this is where the image is going to be projected. I have my 3D world point, and this is the corresponding 2D. So this is the 2D, this is the 3D. Okay, so this X capital bold is a 3D, and this X small bold is the 2D point. The 2D point that has everything, like has the X and the Y component. Okay, and I have a principal ax. So the principal ax is the ray that comes out from the camera center and perpendicular on the image plane. So this is the principal ax, and it intersects with the image plane at something called the principal point. I know too many terms, but you will see why they are important. We're gonna go through it, how to construct it. Okay, so we have the location of the camera, our principal point, which intersects where the principal axis intersects the image plane. We have our 3D and 2D projected. So the first thing, yeah, so this is the world point and the projected point. The first thing to simplify things, this here is like taking, it's as if I'm looking to it from here, from this perspective, okay? So I'm just showing you here similarly, but everything in, to like for simplification of the illustration itself. So let's assume this X ball has X, Y, Z, and 1. So it has the full, like the full point, and I'm only looking at the Y. That's why. So this is for simplification. I'm only looking now at the Y component. Okay. Similarly, here, this X small bolt should have the X and the Y and 1. I'm only going to look at the Y. So this is again for simplification. We're only now taking one component into consideration. What would Y equal to? Remember, this is something from the pinhole model. There are similar triangles here we have. So what do you think? Y is equal to what? Also remember that the distance between the image plane and the camera center is the focal length. So what do you think? Y should be equal to? Let's do similar triangles even. Let's do the ratios for the similar triangles. So Y, so I'm gonna have two ratios that are equivalent because we have some similar triangle. What are they? Yeah, look to it a bit and let me know if you have any suggestions on the chat. Or you can open the mic and directly let me know. Any suggestions on what would be the similar triangles? So I have here the big triangle. And let me change color. And I have here the small triangle. So what do you think would be the ratios in this case? These are similar triangles. Yeah, you can type on the chat, what do you think? So Y over what? What should I consider? So here, this one here, this part is the Y small. And it is equivalent in the bigger triangle to what? Yeah, any, I mean, it's okay. Even if you can just guess from the similar triangles that I had just highlighted, what would be the ratios? I see someone. Yes, thank you, Omar. Exactly. So we have Y over Y is equal to what, Omar? Remember, I have this small triangle and I have the bigger triangle. So these are similar triangles. So the ratio Y small over Y capital should be equivalent to what other ratio?
F over line C, line CZ.
Exactly, which is Z. So this is the depth. Thank you, Rachel. So depth is the distance from our world point to the camera center. And that's exactly, so that's why it's called depth. So this F over Z, exactly, thank you. So we have Y over Y equal F over Z, meaning that the Y, you can simply compute it by taking the focal length and then the Y coordinate in the 3D over the Z coordinate of the 3D world point. Now, if this is the case, we can actually construct it by doing matrix multiplication because we're going always to keep everything as a matrix multiplication. So here, this can give you the same. So if we take the full 3D point and then multiply the x here with f and the y here with the f, the focal length, and then maintain like the z will be our resultant. So we see here, if I take this row and multiply it by the 3D world coordinate, I'll end up with having x here, the 2D. So this is the 2D projected one, is just simply the focal length multiplied by x. And then y is the focal length multiplied by y. But then omega, this is the last, like the homogeneous coordinate component. This one is going to be this row multiplied by the full 3D world point. So it will be equal, omega is gonna be equal to the z. Now, normally, with the homogeneous coordinates, you always normalize, so you always divide by omega. So you will have f the final x. So this is like let's call it the final x. This is going to be fx over omega, which is z. And the final y is just going to be focal length y over z, and then 1. So this will be your resultant homogeneous coordinate point. Okay, we just divided over. I'm not sure if the term normalize is the right term. I don't remember, but like basically trying to like get the homogeneous coordinate component to be 1. So you always divide by that last element. Okay, so this is exactly the same. That's what we wanted. So this is the matrix for it. Anyone has any issue with how we constructed the projection matrix for just describing the pinhole model? Yeah, if no questions, I'll leave it as this and then continue. So this is the very simple part, but things are much more complex than that. So we're not just going to have the focal length. Just here, I'm going to show you that we're going to represent the focal length into this. The projection matrix, we're going to represent it as some small 3x3 matrix. We're going to know what is this 3x3. It is something called intrinsic camera matrix, and I'll explain what this is. Has anyone? Yeah, this is actually a good question. Let me know. Did any of you got is familiar or even just bumped into the term intrinsic or extrinsic camera parameters or camera matrix? Anyone has jumped? No? Okay. If no one, okay, no worries. That's I mean that's good that then we're covering it here. I know it's so this one is a bit more for people working on 3D. So it's not I would say not as popular. But I think it's important even within deep learning, you will see that we will refer. So next time we'll start looking into some of the methods that are actually using some of these components. So yeah, so we'll have this K, which is, we'll understand what this K later, but this is a 3x3 matrix. So this projection matrix is going to be separated into K. So this K here, multiplied by a simple identity. So this is like 1 0 0 0 1 0 0 0 1 and all zeros. So this is what you have here. This is the this is what this representation means. So we have here an identity and a 0 vector. Okay. And then multiplied by, so the X capital bold, this is the 3D world point, and the X small bold, this is the resultant 2D projected point. Okay, so this is again the same. I just showed you this formulation because you will find it in some in a lot of books or even in papers that are relying on it. Now, remember that when we discussed here, this part, which is the Y, we always assumed that this principal point is the origin. I mean, we only got this length, right, from this point here, but the principal point is not always the origin. So now we're gonna add something else. So we'll see that, let's say I have a principal point here that is at location 1, 1. But the real origin, and this is defined based on the camera, like it's a part of the camera parameters. So the real origin is here. This is my 0, 0. So whatever you have defined for the y and the x is actually with respect to this p. But this is not the origin. So what should I do? So this is where it becomes important to take the principal point location into consideration. So this 1, 2, you tell me, if I have this point 1, 2, and I want to compute its location with respect to the origin here. And I know it is 1, 2 with respect to, so this is 1 and this is 2. So it's with respect to this point here. So after transforming, after making sure that it is with respect to the origin, what do you think this will transform into? It becomes what? My principal point is at 1, 1. This point is 1, 2 with respect to P. So this point, let's call it X bold. Now I want to see X bold with respect to P is 1, 2. So X bold with respect to the origin 0, 0 is going to be equal to what? This is the question. What do you think? Intuitively, from looking here, I want to get it with respect to this. So what do you think? Yeah? Exactly. It's going to be 2, 3. Simply you added 1 on the X and 1 on the Y just because the P is 1, 1. Thank you, Rachel. So this is what exactly we will do. So we're going to, based on the location of the P, we're going to add PY and PX as well. Like for the X component, we'll have PX as well added. Okay. So to do this, we're going to have our projection matrix to not include only the focal length. We're going to have PX and PY. So if you take this, like take this row here, multiply by this column, by this vector here, we end up having Fx plus Px multiplied by Z, right? Now, if you take this, and the same, if I take the second row, this is gonna be Fy plus Py multiplied by Z. So I took the second row multiplied by this vector. Now, if I take the last row, this is gonna be just Z. So this is here. And then we talked about how in the homogeneous coordinates, I always tend to divide by the last element to make sure it ends up into 1. So if you divide by the last element, you end up having this, which is what we're talking about. So this is from the pinhole model, and this is adding the principal point in the X. This is pinhole model, adding the principal point from the Y, and this is what we want. So anyone has any issue with how the projection matrix changed? Okay, everything is good. Okay. So now our K, remember this representation we talked about? So this 3 by 3 matrix here not only has the focal length, it also has the principal point. Okay. So that's another thing we need to take into account when doing the projection. But here's the thing. We always assumed this XYZ is already in camera coordinates. So when we started, remember here, I just want to show you, yeah, this point, like the X and the Y with the Z was with respect to the camera center, but that's not necessarily the case. So this is why it's important. And this is, again, like it's very important for people working in robotics or interested to go for it later, or the ones going for 3D vision. They understand these concepts. that you are going to transform from world coordinate. So I have some world coordinate here with its own origin, and I have my point here, and I need to transform it to camera coordinate. So this transformation across coordinates is something we will cover, but let's actually better cover it next time. This is too much. So far we have stopped at just identifying how to use the focal length and the principal point. I don't want to overburden you with too many information at once, so we can stop here. Next time we'll continue the rest of this perspective projection and do a mini practical on it, and see some of the state-of-the-art methods that are actually using it. But yeah, let me first take, is there anyone has any questions or feedback? Like, am I going too fast, too slow? Is it becoming too hard at once? Like, you feel like you want it to be more gradual? Let me know.
I have a question
Yeah,
related to this projection is only over a single axis, right? Not multiple axes. For example, assuming that we are looking like a top view from the z-axis, if it's vertical to xy axis.
Yeah, but this is the thing, Omar. We're not doing orthographic anymore. So for the perspective, actually, we take the full 3D world into account, but we're doing it with respect to the camera center. So we have here X, we have here Y, and we have here the Z component. And we have this 3D world is located here with respect to this coordinate. So this is called the camera coordinate system. When we're going to, if you have a completely different coordinate system, we will have to transform from one coordinate to another. And this is what we will take next time. But it's different than the orthographic. So what you're saying, I think, is referring to the orthographic, where you, let's go back. Oh, sorry, I think I missed it. Yes. So for the orthographic, you completely ignore the depth. Just take the X and the Y as is. So this is what you're talking about?
Yes. Yes. So now we are talking Z, and that's why we are like normalizing with it or dividing over it.
Sorry, can you repeat again this question?
That's why we are taking Z as a component with the equation. We are dividing over it.
Exactly. Yeah, because we are. So this is how the pinhole model works, right? So the pinhole model, you will need to divide by the depth. Like
yes, I'm not familiar with the pinhole model, so I just wanted to make sure this.
Yes, yeah. So but this is one moment, Omar. When I see here, when I'm here talking about the Y, I do exactly the same for the X. I'm not ignoring the depth, and I'm not ignoring the X. So the full projection matrix, you will see here, it's applying both.
Yeah, yes, it's clear. Yes.
Okay, now it's good. Cool. Yeah, anyone else has any questions so far? Okay, so assuming no questions, you can also post questions on the Slack. You can make, if you want to, like, just a personal DM as well, whether for me or Helga, we'll be happy to help you out. Let me just make sure first to stop the recording.